Hi everyone. Today we're going to study direct trigonometric functions or ratios. We have here a right triangle. First, let us label the parts of the right triangle. We can see here the small square that denotes right angle, and the side opposite is what we call the hypotenuse. Then, for the two angles here, let us name one angle to be theta, and the side here is the opposite side of theta. And the last side will be called the adjacent side of the angle theta. We will now specify direct trigonometric functions. We will begin with the sine theta. The symbol for sine is sin theta, and this is equal to the ratio of the opposite side over the hypotenuse. The next function is cosine theta. The symbol is cos, and this is the ratio of adjacent over the hypotenuse. The next function is tangent theta, and the symbol is tan. This is the ratio of the opposite side over the adjacent side. There is a popular mnemonic to help us remember quickly the three functions here. This is the SO, KA, TOA. The SOH is for the sine. The S here is the first letter of the sine. The O is for the opposite, and the H is the hypotenuse. The KA is for the cosine, with that first letter C to denote cosine. The A is adjacent, and H is the hypotenuse. TOA is for tangent, where T is the first letter of the tangent, the O is the opposite, and A is for the adjacent side. So TOA. We'll go now to reciprocal functions. Let's begin with secant theta with a symbol SEC, and this is the ratio of hypotenuse over the adjacent side. This is called reciprocal function because this is the reciprocal of cosine. The next function is cosecant theta with a symbol CSC, and the ratio is hypotenuse over opposite side. This is the reciprocal of the sine. The next function is the cotangent theta, symbolized by COT, and this is equal to the ratio of adjacent over opposite side. This is the reciprocal of the tangent. Let us have example 1. Using the triangle shown below, evaluate sine alpha, cosine alpha, tangent alpha, secant alpha, cosecant alpha, and cotangent alpha. In this triangle, the angle alpha is here. So the opposite side is here with the length 4. This is our right angle, and opposite to that is the hypotenuse with length 5. And the side here is the adjacent side with length 3. Let us now start evaluating the ratios. Let's begin with the sine alpha. The ratio is opposite over hypotenuse. The opposite is 4 and the hypotenuse is 5. So this is 4 over 5. Next is cosine alpha. The ratio is adjacent over hypotenuse. The adjacent side is 3 over the hypotenuse, which is 5. So cosine alpha is 3 over 5. Next is tangent alpha, and the ratio is opposite over adjacent. The opposite is 4 over the adjacent, which is 3. So tangent alpha is 4 over 3. Next is secant alpha. The ratio is hypotenuse over adjacent. Hypotenuse is 5 over the adjacent, and that is 3. So secant alpha is 5 over 3. Next is cosecant alpha. The ratio is hypotenuse over opposite. Hypotenuse is 5 over the opposite, which is 4. So cosecant alpha is 5 over 4. Last is cotangent alpha. The ratio is adjacent over opposite. Adjacent is 3 over the opposite, which is 4. So the cotangent alpha is 3 over 4. So we are now complete with our ratios. Let us have example 2. Given the triangle shown in the figure, find the values of all trigonometric ratios or functions of the angle alpha. The angle alpha is here. We have the length of two sides, 15 and 8. The length of one side is missing. That side is the opposite of the right angle, and that is the hypotenuse. So first, we will calculate for the hypotenuse. We will use the Pythagorean theorem. We will assign letter C to the side which is the hypotenuse, and the formula will be c square equals a square plus b square. Substituting now the values, we have the c square equals 15 square plus the 8 square. Simplifying further, the 15 square is 225 plus 8 square is 64. Then we will add the two numbers, it becomes 289. So c square equals 289. We will get the square root of both sides. Only c will come down here, and we will take the square root of 289, which is equal to 17. So the value c is 17. Then we will start writing our trigonometric ratios. Let's begin with the sine alpha. We know the ratio is opposite over hypotenuse, and that is equal to 8 over 17. The next is the cosine alpha. The ratio is adjacent over hypotenuse. The adjacent is 15 over the hypotenuse 17. So cosine alpha is 15 over 17. The next is the tangent alpha. The ratio is opposite over adjacent. The opposite side is 8 over the adjacent, which is 15. So tangent alpha equals 8 over 15. The next is secant alpha, and the ratio hypotenuse over adjacent. The hypotenuse is 17 and the adjacent is 15. So secant alpha equals 17 over 15. Next is cosecant alpha, and the ratio is hypotenuse over opposite. The hypotenuse is 17 over opposite, which is 8. So cosecant alpha is 17 over 8. Last is cotangent alpha, and the ratio is adjacent over opposite. The adjacent side is 15 over opposite, which is 8. So cotangent alpha is 15 over 8. We have now written all the trigonometric ratios, and this is now the final answer. Example 3. Given tangent A equals 4 over 3. Find the other trigonometric ratios of the angle A. We know that tangent A equals opposite over adjacent. In the problem given is this is equal to 4 over 3. That means opposite or O equals 4 and A equals 3. We have this triangle. This is the angle A. Angle B is a right angle. We have this side 4 and this side here as 3. We need the hypotenuse, which is the H. That is the side AC. By Pythagoras theorem, we write H square equals O square plus A square. We substitute the values 4 square plus 3 square. The right side becomes 16 plus 9, and that is 25. We will take the square root of both sides. So H equals square root of 25, which is simplified into 5. Now let us write the other trigonometric ratios. We begin with cotangent A. That is the reciprocal of tangent. The tangent is 4 over 3. That means cotangent is 3 over 4. Next is the sine of A. That is opposite over hypotenuse. Opposite is 4 over hypotenuse. That is 5. So 4 over 5. Then cosine A, adjacent over hypotenuse. Adjacent is 3, while hypotenuse is 5. So we have 3 over 5. Next is the secant A. This is the reciprocal of cosine. So cosine is 3 over 5. Secant is 5 over 3. And the last is the cosecant A. This is the reciprocal of sine A. Sine A is 4 over 5. So cosecant is 5 over 4. Example 4. Consider triangle ACB, right-angled at C, in which side AB equals 29 units, side BC equals 21 units, and angle ABC equals theta. Determine the value of cosine square theta plus sine square theta. We have the figure here, and we need to find this side, which we write as small b. By Pythagoras theorem, we write 29 square equals 21 square plus b square. We simplify the squares. We have 841 equals 441 plus b square. We transpose the 441 on the left side. It becomes negative. Or we can rewrite this as b square equals 841 minus 441. The difference is 400. When we take the square root of both sides, the square root of b square is b equals the square root of 400, which is simplified as 20. Now let us take the sine theta equals opposite over hypotenuse. Opposite is 20 over 29, and that is the hypotenuse. This is the value of sine theta. For cosine theta, adjacent over hypotenuse. Adjacent side is 21 over hypotenuse, which is 29. Now let us evaluate cosine squared theta plus sine squared theta. When we substitute the values, we have 21 over 29, that is squared, plus 20 over 29, which is squared. When we simplify the squares, we have 441 over 841 plus 400 over 841. When we add these like fractions, we have 841 over 841, which is equal to 1. This is the final answer. Example 5. In a right triangle ABC, right angled at B, if tangent A equals 1, then verify that 2 sine A cosine A equals 1. We have the figure here. We know that tangent A equals opposite over adjacent. In our figure, the angle A is here, and tangent A equals the side BC over side AB, which is equal to 1 based on the problem. That means BC equals AB. We can assign a value here, let's say value K. Now, by Pythagoras theorem, we write the hypotenuse, which is the side AC, which is squared, equals K squared plus K squared. The right side is simplified into 2K squared. Then we will take the square root of both sides. The left side becomes the side AC, that is the hypotenuse, equals the square root of 2K squared, where we can simplify as K square root of 2. Now let us take the sine A, which is opposite over hypotenuse. Opposite is K over hypotenuse, that is K square root of 2. We can cancel the K, and that is now sine A equals 1 over square root of 2. Now cosine A, that is adjacent over hypotenuse. In the figure, that is adjacent equals K over hypotenuse, which is K square root of 2. We can simplify by cancelling the K. So cosine A is 1 over square root of 2. Now let us verify. 2 sine A cosine A equals 1. When we substitute the values, we have now 2 times 1 over square root of 2 times 1 over square root of 2. When we simplify the left side, it becomes 1 equals the right side, which is also 1. Example 6. In triangle OPQ, right angled at P, the side OP equals 7 cm and OQ minus PQ equals 1 cm. Determine the values of sine Q and cosine Q. This is our figure. The side OQ is the hypotenuse. In the given, it says OQ minus PQ equals 1 cm. We can find the value of OQ with respect to PQ. We transpose this negative PQ to the right. So OQ equals 1 plus PQ. By Pythagoras theorem, we have the square of OQ equals square of PQ plus square of OP. We can substitute the values for OQ as 1 plus PQ, that is squared, equals the square of PQ plus the OP is given as 7 cm. So we write here 7 square. We expand the left side, it becomes 1 plus 2 PQ plus the square of PQ equals the right side now square of PQ plus 49. Both sides here have the square of PQ that we can cancel. So we simplify this as 1 plus 2 PQ equals 49. We transpose this constant 1 to the right. It becomes negative 1. So 49 minus 1 is 48. Then from here, we divide by 2. We will get the value of the side PQ, and that is 24. Now for the OQ, that is the hypotenuse, that is 1 plus PQ. We substitute the value of PQ as 24. We will get the value of OQ. So that is OQ equals 1 plus 24, which is 25. And we can write it here also. Now let us get the sine Q, which is equal to opposite over hypotenuse. In our figure, the Q is here. So opposite is 7 over hypotenuse, which is 25. This is the value of sine Q. For the cosine Q, we have adjacent over hypotenuse. Adjacent is 24 over hypotenuse, which is 25. This is now the value of cosine Q. Hi everyone, today we're going to study trigonometric ratios of 45 degrees. Given this right triangle with a right angle at B, so we know that the angles A and C are complementary, meaning the sum is equal to 90 degrees. Suppose we assign A as 45 degrees. We know that the angle C equals 45 degrees also. So the angles A and C here are equal. It follows that the side BC is equal to the side AB. Suppose we assign values for these equal sides. Say equals K. So we write here K, and here also is K. By Pythagoras' theorem, we can get the value of the hypotenuse. That is the AC. So, the square of AC equals K square plus K square. The right side is now 2K square. And let us take the square root of this equation. The left side is now the value of the hypotenuse. That is the AC. And that is equal to the square root of 2K square. We can simplify the right side as K square root of 2. Let's write the value in the hypotenuse of the figure. Now from the figure, let's consider angle A. This is the 45 degrees. Let us take the sine of the angle A, or we say the sine 45 degrees. We know that this is opposite over hypotenuse. When we get the values from this triangle, we have K over K square root of 2. We can simplify the fraction by cancelling the K. So it becomes 1 over square root of 2. This is the sine 45 degrees. What about the cosine of A? Or we say cosine 45 degrees. This is adjacent over hypotenuse. From the figure, we can get the values as K over K square root of 2. We simplify further this fraction, we cancel the K, and that will be 1 over square root of 2. This is the cosine 45 degrees. Please observe that sine 45 degrees is equal to the cosine 45 degrees. Both are 1 over square root of 2. What about the tangent of A? Or we say tangent 45 degrees. Tangent is opposite over adjacent. From the figure here, we can write K over K, which is simplified into 1. This is the tangent 45 degrees. Now let us write the remaining 3 trigonometric ratios. Let's begin with secant A or secant 45 degrees. We know that secant is the reciprocal of cosine. So secant 45 degrees is the reciprocal of this value. So this is equal to square root of 2. What about cosecant of A or cosecant 45 degrees? We know that cosecant is the reciprocal of sine. So we'll just take the reciprocal of this value. So this will be equal to square root of 2. Note also here that the secant 45 degrees is equal to the cosecant 45 degrees. Both of them are equal to square root of 2. Now, cotangent 45 degrees. Cotangent is the reciprocal of tangent. Tangent 45 degrees equals 1. So the reciprocal of 1 is 1 also. This is our cotangent 45 degrees. So we have now here the values of trigonometric ratios of 45 degrees. Hi everyone, today we're going to study trigonometric ratios of 30 degrees and 60 degrees. Let this triangle ABC be an equilateral triangle. Since each angle in an equilateral triangle is 60 degrees, therefore this angle A is equal to angle B and is equal to angle C, all of them equal 60 degrees. So we can write the angle B to be 60 degrees. Now let us draw the height of this triangle with this AD. In this case, we're going to divide the angle A into 2. Here is 30 degrees, the other 30 degrees on the other side. Now, we let the side AB and BC and side AC be equal to 2A. In that case, the side BD equals A. Now look at the triangle ADB. By Pythagoras' theorem, we can write the square of 2A, that is the hypotenuse, equals A square plus the side AD, that is squared. The left side is 4A square equals A square plus the square of AD. This A square we transpose to the left. And the difference of the left side is 3A square equals the square of AD. In here, we will take the square root. So AD equals the square root of 3A square. And this is simplified into A square root of 3. This is the height of the triangle. Now let us write the trigonometric ratios of 30 degrees. Let's begin with sine 30 degrees. We know that sine equals opposite over hypotenuse. Looking at the figure, the 30 degrees is here. So we write the values. The opposite is A over 2A, which is the hypotenuse. We can simplify this as by cancelling A. So it becomes 1 over 2. Next, cosine 30 degrees. Cosine is adjacent over hypotenuse. In the figure, we get the values as adjacent is A square root of 3 over hypotenuse is 2A. We can cancel the A and this is simplified into square root of 3 over 2. Next, tangent 30 degrees. Tangent is opposite over adjacent. In the figure, opposite is A over adjacent, that is A square root of 3. When we cancel the A, we have 1 over square root of 3. Now let's go to secant 30 degrees. We know that secant is the reciprocal of cosine. Cosine 30 degrees is this value, square root of 3 over 2. Therefore, for secant 30 degrees, we take the reciprocal, and that is 2 over square root of 3. Next is cosecant 30 degrees. Cosecant is the reciprocal of sine. The sine 30 degrees is 1/2. Therefore, the cosecant 30 degrees is 2. Now let's have cotangent 30 degrees. Cotangent is the reciprocal of tangent. Tangent 30 degrees is 1 over square root of 3. Therefore, the cotangent 30 degrees is square root of 3. Now let's have the trigonometric ratios of 60 degrees. Let's begin with sine 60 degrees. In our figure, the 60 degrees is here. So, for sine 60 degrees, that is a square root of 3 over 2a. When we simplify by cancelling the a, we have square root of 3 over 2. Next, cosine 60 degrees. This is adjacent over hypotenuse. So we write a over 2a. That we simplify as 1 over 2. Next is tangent 60 degrees. Opposite over adjacent. So that will be a square root of 3 all over a. We cancel the a, it becomes square root of 3. Next is secant 60 degrees. We will take the reciprocal of cosine 60 degrees. And that value is now 2. For cosecant 60 degrees, we will take the value of the reciprocal of sine 60 degrees. So we have here 2 over square root of 3. For cotangent 60 degrees, we will take the reciprocal of tangent 60 degrees. So the value now is 1 over square root of 3. These are the values for trigonometric ratios of 60 degrees. Now take note that sine 30 degrees is equal to cosine 60 degrees. Also, cosine 30 degrees is equal to sine 60 degrees. Example 1. In triangle ABC below, right-angled at B, determine the lengths of the sides BC and AC. This is our figure. Let's begin by solving the side BC. Given here is the angle 30 degrees. Side AB is 5 cm. This side is the opposite of the angle C. We want to look for the side BC. BC here is the adjacent side of the angle 30 degrees. Let us relate the opposite and the adjacent sides with respect to the given angle 30 degrees. So we write tangent 30 degrees equals 5 over the side BC. The tangent 30 degrees is equal to 1 over square root of 3. Then we cross multiply to get the value of BC. So that will be BC equals 5 square root of 3. The unit of measurement is centimeter. Now let us solve for the side AC. The side AC here is the hypotenuse of the triangle. So let us relate the opposite side with regard to the hypotenuse with respect to the given angle 30 degrees. So we write sine 30 degrees equals 5 over AC. The sine 30 degrees is 1/2. Let us cross multiply to get the value of AC. That will be AC equals 10. The unit of measurement we will write centimeter. Example 2. In triangle PQR, right-angled at Q. Determine angle P and angle R. We can see here that the side PQ is 3 cm and the hypotenuse is 6 cm. Let us solve for angle P. The angle P is here. Let us relate the angle P with regard to the given sides. The sides are the adjacent and the hypotenuse. So we write cosine P equals 3/6, where we simplify as 1/2. We know that cosine 60 degrees equals 1/2, and cosine P equals 1/2. Therefore, P equals 60 degrees. We have now the value of the angle P. Now, let us find the angle R. Angle P and angle R are complementary angles, meaning the sum is 90 degrees. Since P equals 60 degrees, we can have the value of R equals 30 degrees. Example 3. If sine of the angles A minus B equals 1/2, the cosine of the angles A plus B equals 1/2. The A plus B is more than 0 degree, but less than or equal to 90 degrees. Given also that A is more than B. Find A and B. We know that sine 30 degrees equals 1/2. Given here is sine of the angles A minus B equals 1/2. Therefore, the sine A minus B equals sine 30 degrees. We can simplify this further as A minus B equals 30 degrees. Let this be equation 1. Also, we know that cosine 60 degrees equals 1/2. In the given, we say the cosine A plus B equals 1/2 also. Therefore, the cosine A plus B equals the cosine 60 degrees. Then we can simplify this as A plus B equals 60 degrees. Let this be equation 2. Now let us put together the two equations and let us solve for the A and B respectively. Let us add the equations. When we do that, the B variable will be cancelled out. So A plus A will be 2A equals 30 plus 60 equals 90 degrees. We can divide this equation by 2 to get the value of A. So A equals 45 degrees. We have now this value of A. Let's go for the value of B. From equation 1, we can write and substitute the value of A. So it becomes 45 degrees minus B equals 30 degrees. This negative B we can transpose to the right, and this 30 degrees we transpose to the left. So we have now like this. On the left side, the difference is 15 degrees. So we can write B equals 15 degrees. This is now the value of angle B. Hi everyone, today we're going to study trigonometric ratios of 0 degree and 90 degrees. Let's begin with trigonometric ratios of 0 degree. In the triangle ABC here, look at what happens to the trigonometric ratios of angle A. If angle A is made smaller and smaller till it becomes 0. So this is our final figure. As angle A gets smaller and smaller, the length of the side BC decreases. The point C gets closer to point B, and finally, when angle A becomes very close to 0 degree, the side AC becomes almost the same as side AB. Now let us use our final figure here to compute for the trigonometric ratios of 0 degree. Let's begin with sine 0 degree. We know that sine is opposite over hypotenuse. Using our final figure here, that will be BC over AC. We can see that the BC equals 0 over the side AC. So we simplify this as 0. That means sine 0 degree is 0. Now cosine 0 degree. Cosine is adjacent over hypotenuse. In the figure, we can see that will be AB over AC. We can notice that AB equals AC in this figure. Therefore, this is equal to 1. So cosine 0 degree equals 1. Next, tangent 0 degree. Tangent is opposite over adjacent. So that will be BC over AB. In the figure, we can see that BC equals 0. Divide by AB, that will be 0. Therefore, tangent 0 degree is 0. Next is the secant 0 degree. Secant is the reciprocal of cosine. Since cosine 0 degree is 1, so secant 0 degree is 1 also. Next is cosecant 0 degree. Cosecant is the reciprocal of sine. So in the figure, we can write here AC over 0. Division by 0 is undefined. Therefore, cosecant 0 degree is undefined. Next, cotangent 0 degree. Cotangent is the reciprocal of tangent. So in the figure, we write here AB over 0, and this will be equal to undefined also. So cotangent 0 degree is undefined. These are the trigonometric ratios of 0 degree. Now let's have trigonometric ratios of 90 degrees. Let's have this triangle. In the triangle ABC here, look at what happens to the trigonometric ratios of angle A. If angle A is made larger and larger till it becomes 90 degrees. So the figure becomes like this. This is now our final figure. As angle A gets larger and larger, the angle C gets smaller and smaller, and the length of the side AB decreases and closes to 0. Finally, when angle A becomes very close to 90 degrees, the side AC becomes almost the same as side BC. Now let us use our final figure to compute for the trigonometric ratios of 90 degrees. Let's begin with sine 90 degrees. We know that sine is opposite over hypotenuse. Using the values of the figure, this is BC over AC. We can observe that AB equals AC. So, the sine 90 degrees equals 1. Next, cosine 90 degrees. Cosine is adjacent over hypotenuse. In a figure, we can write AB over AC. We can observe that the AB equals 0. So 0 divided by AC is 0. Therefore, cosine 90 degrees is 0. Tangent 90 degrees. Tangent is opposite over adjacent. Using the values of the figure, that will be BC over AB. But AB equals 0. Therefore, BC divided by 0 is undefined. So, tangent 90 degrees is undefined. Then we have the secant 90 degrees. Secant is the reciprocal of cosine. Using the figure, we have AC over 0. And secant 90 degrees is undefined. What about cosecant 90 degrees? Cosecant is the reciprocal of sine. Since sine 90 degrees is 1, therefore cosecant 90 degrees equals 1 also. Then cotangent 90 degrees. Cotangent is the reciprocal of tangent. Using the figure, we can write 0 over BC. And this will be 0. These are now the trigonometric ratios of 90 degrees. Hi everyone! Today we're going to study Pythagorean identities. An equation is called an identity when it is true for all values of the variables involved. Similarly, an equation involving trigonometric ratios of an angle is called a trigonometric identity if it is true for all values of the angles involved. Let us discuss here one trigonometric identity that is called Pythagorean identities. Let's have this right triangle ABC. Then we will use this acute angle A later as reference. By Pythagoras' theorem, we can write the square of side AB plus the square of the side BC equals the square of the hypotenuse, which is AC. Let this be equation 1. There are three Pythagorean identities. Let us derive the first one. Let us divide the equation by the square of the side AC. So equation becomes like this. Then let us simplify. It becomes the square of AB over AC plus the square of the fraction BC over AC equals the right side becomes 1. Now in reference to angle A, AB over AC is adjacent over hypotenuse, that is squared, plus BC over AC is opposite over hypotenuse, that is squared, then equals 1. Remember that adjacent over hypotenuse is cosine A, that is squared, plus opposite over hypotenuse is sine of A, that is squared, equals 1. We can rewrite this equation as sine square A plus cosine square A equals 1. This is the first Pythagorean identity. This is true for all angle A such that A is more than or equal to 0 degree and A is less than or equal to 90 degrees. Let us copy this identity down here. Now let us derive the second Pythagorean identity. Let us divide equation 1 by the square of AB. So equation 1 becomes like this. When we simplify this equation, the first fraction here is cancelled out. It becomes 1 plus the square of the fraction BC over AB equals the square of the fraction AC over AB. Now in reference to angle A, this BC over AB is opposite over adjacent, that is squared, equals AC over AB is hypotenuse over adjacent, that is squared. Remember that this opposite over adjacent is tangent A, that is squared. The hypotenuse over adjacent is secant A, that is squared. Then we rewrite this equation as 1 plus tangent square A equals secant square A. This is the second Pythagorean identity. This is true for all angle A such that A is more than or equal to 0 degrees, but A is less than 90 degrees. Let us copy the second equation down here. Now let us derive the third Pythagorean identity. Let us divide equation 1 by the square of the side BC. So equation 1 becomes like this. Then let us simplify. The second fraction here will cancel out into 1. The first fraction is now square of AB over BC equals the square of AC over BC. In reference to angle A, AB over BC is adjacent over opposite. This AC over BC is hypotenuse over opposite. Remember that adjacent over opposite is cotangent A, that is squared, then plus 1 equals hypotenuse over opposite is cosecant A, that is squared. We can simply rewrite this equation into cotangent square A plus 1 equals cosecant square A. This is the third Pythagorean identity. This is true for all angle A such that A is more than 0 degree, but A is less than or equal to 90 degrees. These are the Pythagorean identities. Example 1. Express the ratios cosine A, tangent A, and secant A in terms of sine A. Let's begin with cosine A. Remember that by Pythagorean identity, we have sine square A plus cosine square A equals 1. Let us isolate the cosine. Let us transpose the sine square A to the right. So we have cosine square A equals 1 minus sine square A. Then we will take the square root of both sides. The left side becomes cosine A equals, the right side is plus or minus the square root of the quantity 1 minus sine square A. Since we are dealing with acute angle A, so the cosine A will take the positive value of the square root of 1 minus sine square A. So this is the value of cosine A in terms of sine A. Then we'll have the tangent A. We know that tangent A equals sine A over cosine A. Now, let us substitute the cosine value from this equation into here. So it becomes tangent A equals sine A over the square root of the quantity 1 minus sine square A. This is the value of tangent A in terms of sine A. Then let's have the secant A. We know that secant is the reciprocal of cosine. So we write secant A equals 1 over cosine A. And from here, let's substitute the cosine A value from this equation. So we have secant A equals 1 over the square root of 1 minus sine square A. This is the secant A in terms of sine A. Example 2. Prove that secant A times the quantity 1 minus sine A times secant A plus tangent A all equal to 1. Let us copy this problem down here. Now let us simplify the left-hand side. What we're going to do here is we express all ratios in terms of sine or cosine. So this secant A becomes 1 over cosine A. times 1 minus sine A times the secant A here becomes 1 over cosine A plus the tangent A becomes sine A over cosine A equals 1. From here we multiply this 1 over cosine A by this 1 minus sine A. It becomes like this. And inside we combine the like fractions. Cosine A is common. So we have 1 plus sine A over cosine A. Let us now multiply the two fractions. So we have 1 minus sine square A all over cosine square A. From here, remember that we have Pythagorean identity. Sine square A plus cosine square A equals 1. We can isolate cosine square A, so we have 1 minus sine square A. Notice that the right-hand value here is the numerator of our fraction here. So we can substitute cosine square A in the numerator. So it becomes like this. The cosine square A in the numerator is now the same with the cosine square A in the denominator, where we can cancel this. So it becomes 1, which is equal to the right-hand side, which is also 1. Example 3. Prove that cotangent A minus cosine A all over cotangent A plus cosine A equals cosecant A minus 1 all over cosecant A plus 1. Let us simplify the left-hand side. So the fraction on the left hand we will write in here. Next, we're going to express all ratios in terms of sine or cosine. Looking at our fraction, we will change this cotangent A into sine or cosine ratios. So cotangent A is cosine A over sine A. We substitute in the numerator and in the denominator. Now look at the numerator. The fraction and this negative cosine A have something in common, which is the cosine A. Same is true with the denominator. Let us factor out the common, that is cosine A. So it becomes like this. Cosine A times the quantity 1 over sine A minus 1 all over cosine A times the quantity 1 over sine A plus 1. In the numerator and denominator, common is cosine A. We can cancel it out. And we know that 1 over sine A is cosecant A. So we change it here. So we have now cosecant A minus 1 all over cosecant A plus 1. From here we stop because this value is now equal to the right-hand side. Example 4. Prove that sine theta minus cosine theta plus 1 over sine theta plus cosine theta minus 1 equals 1 over secant theta minus tangent theta. Using the identity secant square theta equals 1 plus tangent square theta. Let us simplify the left-hand side, meaning let us copy the left-hand side fraction here. Our goal now here is to make this value equal to the right-hand side. Let us now divide each of the terms by cosine theta. So it becomes like this. And then we simplify each of the fractions one by one. The sine theta over cosine theta is tangent theta minus, this is cancelled out, plus secant theta over, in the denominator is tangent theta plus 1 minus secant theta. Let us rearrange the terms. We can put together the tangent theta and secant theta closer. So it becomes like this. And from here, let us multiply this by the conjugate of tangent theta plus secant theta, which is tangent theta minus secant theta. Same value we will put in the denominator. So what we'll do here, we will multiply this numerator in this group and then in the negative one. So it becomes like this. Tangent squared theta minus secant squared theta minus the tangent theta minus secant theta. In the denominator, we'll just put them together. And from here, let us look at our identity. We can put together the tangent and the secant in one side. And this constant one, we will put on the left. So it becomes negative 1 equals tangent squared theta minus secant squared theta. Look at this group here. It is the same with the right-hand side value, which means we can substitute negative 1 to this value here. So it becomes like this. And then let us simplify the numerator. We have negative 1 minus tangent theta plus secant theta. In the denominator, we have this trinomial here. Next thing to do, let us manipulate our numerator. Let us rewrite this as the negative of the group tangent theta minus secant theta plus 1. From here, we can see that this value here is the same with the trinomial in the denominator that we can cancel. When we do that, it becomes negative 1 over tangent theta minus secant theta. Let us now rewrite our denominator as negative 1 times secant theta minus tangent theta. So we can cancel the negative 1 in the numerator and in the denominator. When we simplify, it becomes 1 over secant theta minus tangent theta. From here we stop because it is already equal to the right-hand side value here. This is now the final answer.